Hi, welcome back to General Chemistry, Chapter 7 with Jim Burnham. Today we are talking about chemical quantities. Let's recap. 2 chapters ago, Chapter 5, we talked about atoms and elements that form the periodic table. And these are the building blocks for basically everything else, all the compounds the millions and millions of compounds that we study in chemistry. In Chapter 6, we looked at the chemical names and formulas. And so it's the stuff we can build out of those elements. So the elements like the building blocks, the compounds, and molecular compounds, ionic compounds are like the things we can build out of them. And in this chapter, we want to talk about chemical quantities, how we quantify, how we measure, how we weigh these compounds. So this takes us to one of my favorite topics and one of the most important topics in chemistry, and that's the concept of the mole. The mole as a measurement of matter. This is section 1 of chapter 7. So first let's back up. How do we count many things? We have lots of words when we count things by more than one. So a pair is 2, a pair of pairs. A dozen is 12. What's a baker's dozen? 13. What's a gross? It's 12 twelves, or 144. What is a ream, like a ream of paper? 500. So we have these ways of counting things in chunks. But what if we're talking about something really, really large, where the quantities are just astronomical, like grains of sand? Is it practical to count each and every single grain? Of course not. So how else could we measure or quantify the sand? Well, we could calculate its mass. How much does it weigh? We could calculate its volume. How much space does it take up? Let's consider something simple like apples. We can measure apples in 3 ways. At a fruit stand, they might be sold by the individual count, say 5 for $2. At a grocery store, they might be sold by weight, say 89 cents a pound. At an orchard, they might be sold by volume, $9 a bushel, say. So all of these, count and mass and volume, they can be equated to a dozen apples. We can convert the count to a dozen, the mass to a dozen, and the volume to a dozen. So we can relate them all to that central term. So by count, a dozen apples equals 12 apples. By mass, a dozen apples equals 2 kilograms, approximately. A dozen apples equals 2/10 of a bushel of apples. And so we can now convert between these units using their relationship to that common term, the dozen apples. So we could calculate the mass of a bushel of apples, or say the mass of 90 apples. So what would be the mass of 90 apples? Well, let's use those conversion factors that we developed before. So 1 dozen apples per 12 apples, 2 kilograms of apples per dozen apples. And so creating our conversion factors, we could say 90 apples times those appropriate conversion factors would give us 15 kilograms of apples. And we would cancel out all of our the units we don't want for the units that we do want. So we go from an individual count through a dozen to the weight per dozen to the weight of the apples. All right, well, how about counting something like atoms and molecules, which are even tinier than grains of sand? How are we going to count those? So this is the concept of the mole. Now, what is a mole? Is it this cute guy? Unfortunately not. Is it this not so cute guy? Is it this scene?
Holly Goodwin. Yes, nice to meet you. Nice to meet you, Mo.
Nice to meet you, Mo.
Don't say Mo.
Don't say Mo.
I said Mo.
I said Mo. Stop.
Bye, Mo.
Bye, Mo.
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 Shut up!
Mole, mole,
Mole, mole, mole, mole, mole.
Mole, mole, mole. No, it's not that. We can count really, really large quantities, like a bunch of jelly beans or a bunch of nuts and bolts or a bunch of paper clips, by using something that I've developed called WWCD. What would criminals do? So let's say you have a bunch of dope to sell. This is all hypothetical. Of course, you would never do this. It's illegal. And you need to get paid in cash because, well, that's what criminals do. So how do the criminals count all this cash? Well, they don't have time to, count each and every dollar bill. They're in a warehouse. It's late at night. They're short on time. The cops might be coming. They weigh it. $100 bills. $1 million of $100 bills weighs 22 pounds. So if you sell $1 million worth of drugs, you should get paid in a suitcase that has a net weight in bills, $100 bills of 22 pounds. Now you know, and you're welcome very much. As you know, atoms and molecules are incredibly small, inconceivably small, so small they're inconceivable. And yes, of course, I have to give you this clip from The Princess Bride.
Inconceivable. You keep using that word. I don't think it means what you think it means.
But we can still count these inconceivably small molecules and atoms by weighing them. How many molecules of water would you guess are in 18 grams of water, which is just a little over an ounce? Hundreds? Thousands? Millions? Billions? Trillions? Surely it must be in the trillions, right? How about quadrillions? How about quintillions? How about hextillions? Yep. 602 hextillion molecules of water in 18 grams. That's 602 followed by a bunch of dang zeros. In scientific notation, we say 6.02 times 10 to the 23rd. We call that number a mole. It's also known as Avogadro's number, named after this guy, Avogadro. He didn't invent the term, but it was named to honor him. He invented some other cool stuff. So this means we can count the number of water molecules based on weight, even though we can't possibly count them molecule by molecule. How big a number is a mole? Well, a mole of animal moles would cover the earth with a layer more than 8 million animal moles thick. That is a lot of moles. Lined up end to end, a mole of animal moles would stretch from the Earth to the nearest star, Alpha Centauri, which is 4 light years away. That's the distance light can travel in a year. And light travels 186,000 miles per second. So in 4 light years, you could get to Alpha Centauri. Well, a mole of moles would stretch between the Earth and Alpha Centauri more than 2 million times. You can make 2 million chains between us and 4 light years away. It's a ridiculous distance. So a mole is an astonishingly large number. And why that particular number? Well, we need a number unit that gives us a usable amount of atoms or molecules or formula units, as we'll see later. And that particular number, 6.02 times 10 to the 23rd, is the number of atoms or molecules or formula units equal to that atoms or molecules or formula units atomic mass number in grams. So it's equal to the mass number in grams of whatever atoms or atoms that we're talking about. What is atomic mass? Well, as you know from your knowledge of the periodic table, that every element has a certain weight. We call that an atomic mass unit. And it is the average of all the isotopes of that particular atom. So it's the weighted average of all the isotopes of that particular atom. So here's carbon. Carbon's atomic mass is 12. And we know that it's built out of 12 protons, 12 neutrons, and 12 electrons, but the electrons don't weigh hardly anything. They're 1/2 2,000th of the weight of the protons and the neutrons. So essentially all of the weight of an atom comes from the protons and the neutrons. And so carbon has 6 neutrons, 6 protons for an atomic mass of 12. Now these are atomic mass units when we're just counting the weight essentially of each proton and neutron. And we call this carbon 12. So the idea is that let's pick an amount of carbon that weighs the same as its atomic mass in grams. And so let's figure out what is the number of carbon atoms that weigh 12 grams. And the number of atoms in 12 grams of carbon 12 turns out to be the mole. This astonishingly large number, 6.02 times 10 to the 23rd, or 602 hextillion atoms. So a mole essentially is 6.02 times 10 to the 23 of anything. So it's a lot bigger than any of the numbers we've talked about. Gross and reams and dozens. Think of the mole as a chemist's dozen. But instead of, a baker's dozen, which has 13, a chemist's dozen has 6.02 times 10 to the 23, 602 hextillion of whatever it is we're counting. So now we need to introduce a new term. The term is called representative particle, and it refers to the species present in the substance. And the substance we're usually considering is going to be either atoms or molecules or formula units, the ions that make up ionic compounds. So that's all we're referring to here. A representative particle is whatever is the representative. So if it's an element, it's going to be the atom. If it's a molecular compound, it's going to be the molecule. If it's an ionic compound, it's going to be the formula unit. That's what we mean by representative unit. So for most elements, it's the atom. Well, helium is composed of helium atoms. Iron is composed of iron atoms. There are 7 elements, however, that exist as diatomic molecules. These are our old friends, Brinkelhoff. But we also have another one that I'll introduce to you that I found that I thought was good. Have no fear of ice-cold beer. That might be easier to remember than Brinkelhoff. Have no fear of ice-cold beer. These are the 7 elements that exist in diatomic form. So rather than the single elements, they exist in groups of 2. So the representative unit of these 7 diatomic molecules, and all molecular compounds is the molecule. So the representative element for elements is atoms. The representative element for molecules, or diatomic molecules, any kind of molecule, molecular compound is the molecule. And the representative unit for ionic compounds is going to turn out to be the formula unit. So here are examples of representative particles. What's our substance? Iron. Okay. Iron is an element, so the representative particle is an atom, and we represent it with the formula Fe. Nitrogen gas is a diatomic molecule, so its representative particle is the molecule, and then here's its formula. Water is a molecular compound, so its representative particle is going to be the molecule. Here's its formula. A calcium ion, we say the representative particle here is the ion, and we represent it this way. How about an ionic compound? Well, the representative particle here would be the formula unit, and so we represent it this way. Again, glucose, a molecule, represented this way. So we can count particles in moles, and by that we are counting the representative particles. So if we're talking about atoms, that's the smallest unit of an element, or we can talk about molecules, which is the smallest unit of a molecular compound, or we can talk about formula units, the smallest unit of an ionic compound. In all those cases, we count by weight. So a mole of carbon-12 is exactly 12 grams. A mole of copper with an atomic mass of 63.5, a mole of it equals 63.5 grams. So a mole is equal to the atomic mass of whatever we're considering in grams. So whatever its atomic mass unit is, we say we're going to convert that into grams. And it takes 602 hextillion, not molecules, atoms of carbon-12 to give us 12 grams. It takes 602 hextillion copper atoms to give us 63.5 grams. But in both of these, by weight, see, even though the weights are different, their individual count is the same. They both contain 6.02 times 10 to the 23. So a mole is an amount of something that is equal to its atomic mass in grams. Let me repeat that. A mole is an amount of something that is equal to its atomic mass in grams. Or, there's a fancy word for it, gram atomic mass. So when we're talking about atoms, we talk about gram atomic mass. The atomic mass of the element in grams. Remember, we talked about atomic mass units to express the weight of a single atom. Atomic masses are the weighted average of all the isotopes of that element. So, as this is all repeat, an average carbon atom, which is 12 atomic mass units, 6 protons, 6 neutrons, it's 12 times heavier, it's heaviers than the average hydrogen atom, which has an atomic mass unit of 1. So if you think about it, if every carbon atom is 12 times heavier than the hydrogen atom, then 100 carbon atoms is 100 times heavier than 100 hydrogen atoms. And any number of carbon atoms will be 12 times heavier than the same number of hydrogen atoms. So 12 grams of carbon and 1 gram of hydrogen contain the same number of atoms, namely Avogadro's number, the mole, 6.02 times 10 to the 23rd. So we can use the mole as a conversion factor. We can say that 1 mole is equal to 6.02 times 10 to the 23 particles, whether those particles are atoms or molecules, unit formulas for ionic compounds. Or we can flip it around and put it particles over moles. And notice that a particle can be an atom, a molecule, a formula unit, or an ion. How many atoms are contained in the gram atomic mass of any element? So if you get the atomic mass in grams of any element, it's going to be a mole. 6.02 times 10 to the 23 atoms. So 12 grams equals the gram atomic mass of carbon-12. Therefore, 12 grams equals a mole of carbon-12. And 1 gram of hydrogen equals a mole of hydrogen, because that is its atomic mass in grams. And 24.3 grams of magnesium, which is the gram atomic mass, or the atomic mass of magnesium in grams, 24.3 grams of magnesium equals 1 mole of magnesium. So we can have moles of anything, not just atoms. Molecules, ions, ionic compounds, basketballs, donuts. We typically don't count those in those things because that's just such a massive quantity. For molecules, we just have to find the molecular mass in grams. Okay, so when we're talking about atoms, we talk about atomic mass in grams. For the molecule, we have to find the mass of the whole molecule. How do we do that? Well, we just add up the atomic mass in grams for each element in the compound. So what's the mass of a mole of H2O? Well, we have 2 H's. So what's the atomic mass in grams for those? So that's 2 grams. Here's oxygen. Its atomic mass is 16, so its atomic mass in grams would be 16 grams. So 1 plus 1, that's 2, plus 16, 18. So we have 1 oxygen, 2 hydrogens. We look at the atomic masses. Here's 16, here's 1. We turn it into grams. 16 grams of oxygen, 2 grams of hydrogen, for a total of 18 grams. This is called the gram molecular mass, which should be very similar to the gram atomic mass that we discussed a second ago. So a mole of H2O is 18 grams of H2O, and conversely, 18 grams of H2O is equal to a mole. So now we can convert between weight and the number of molecules. We can count by weight. So if we know the amount of grams we have, we can divide the number of grams by the molar mass and get the number of moles that we have. If I have 18 grams of water and I know that there's 18 grams in a mole, then I have 1 mole. And I know that 1 mole is Avogadro's number of atoms or molecules. So I would have 6.02 times 10 to the 23rd molecules of water if I had 18 grams of water. So I can convert from number through moles to weight and back and forth. Can we have moles of ionic compounds? Yeah, you can have moles of anything. But of course, since the representative particle of an ionic compound is the formula unit, not the molecule, we don't call it a gram molecular mass. The gram, we call it a formula mass. So a mole of an ionic compound is defined as the gram formula mass, the mass of the formula in grams. And we find it the same way as gram molecular mass. We add up the atomic masses in grams of the ions in the formula. So what's the gram formula mass? That just means the formula mass in grams for calcium iodide. We have one calcium atom and we have two iodide atoms, or iodine atoms. So we look up here, calcium over here is about 40.1 atomic weight. So we take its atomic mass in grams, and we look over here at iodine. Iodine is 127 essentially, and we take its atomic mass in grams as well, and we have two of those. So we take 40 grams of calcium and 2 times 126.9 grams of iodine, and we get 293.9 grams of calcium iodide. So how many formula units would this represent? Would this weight represent? It would represent a mole, 6.02 times 10 to the 23rd, a mole of calcium iodide. Let's go back to water for a second. What would 36 grams of water equal? Well, we know that 18 grams is 1 mole, so 36 grams would have to be 2 moles. Okay, here's our key concept. Moles allow us to count inconceivably large numbers by weighing them. So the bottom line, a mole of any atom or molecule or ion or ionic compound is a quantity that equals its atomic mass in grams. So we count up the atoms, the number of atoms, and we take their atomic mass in grams and we total all of that up. And that total in grams gives us the total, that gives us the moles of an atom, or the moles of a molecule, or the moles of an ion, or the moles of an ionic compound. So we could calculate a polyatomic ion's weight by adding up the atomic masses of each of the elements that make up that polyatomic ion. Here's a mole of several substances. So as you can see, here's our 18 grams of water, and here's a mole of mercury, and a mole of glucose, a mole of lead, and copper, and salt, and sulfur. And here's an ionic compound, potassium dichromate, I think that is. These all have the same number of atoms, or molecules, or formula units. How many is that? 6.02 times 10 to the 23rd. So we also learned these 3 important related terms. Molar mass, it's the mass in grams of 1 mole of the substance. And it can be the gram atomic mass, it can be grams for molecular mass, it can be the gram formula mass. So, and this is just the atomic mass, the mass of the atoms in grams, the mass of all of the molecule in grams, the mass of the formula in grams. Just read it backwards if that helps. All of which equal a mole of the representative substance. So if you have an amount of grams equal to the atomic mass of an atom, you have a mole of that atom. If you have an amount of grams of a molecule equal to its molecular mass, the weights of all of its, the atomic weights of all of its molecules in grams, then you have a mole. So let's use a term that encompasses all 3 of these, and that's molar mass. Molar mass is, we'll just say the molar mass is any of these. It's the mass of an atom, a mole of atoms. It's the mass of a mole of molecules. It's the mass of a mole of formula units. So molar mass. So now, let's do some critical thinking. In your own words, what is a mole? Okay, it's the amount of a substance that contains 6.02 times 10 to the 23 representative particles of that substance. It's the amount of something that has 602 hextillion pieces of that substance. What is the molar mass of any substance? Well, it's the mass in grams of 1 mole of the substance. The mass in grams of 1 mole. And that's going to be equal to the sum of its total atoms in grams. So just like if you have 12 grams of carbon, you have a mole of carbon. If you have 12 grams of carbon plus, anyway, you get the idea. So, critical thinking. Can we use moles to count anything? Or just atoms and molecules and ions and ionic compounds? Well, of course, we could use moles to count anything, but it's especially appropriate to use them to count these things because these things come in such incredible tiny quantities. And so even just a tiny handful of them is going to be an astonishingly large number. So we need some unit that can accommodate that and give us a usable amount, a weighable amount. Oh, and that's why it's especially useful counting atoms and molecules in formula units. Could we define the mole in terms of ounces or pounds instead of the way we do in terms of grams? Now think about that. What if we just said we're going to, instead of saying that a mole of carbon 12 is 12 grams, the amount of grams equal to its atomic mass, what if we said the mole is going to be defined as 12 ounces of carbon 12 or 12 pounds of carbon 12? Could we define the mole that way? There's no reason why we couldn't. We could define the mole in terms of ounces or pounds or grams. They're all just arbitrary numbers. We're just trying to get from this infinitesimally small thing enough of them together that we can count them by weight. And so if that weight is grams, great. Now what would happen if we counted by ounces or pounds instead of grams? Would our number change? Yeah. Because an ounce is heavier than a gram, so it would take more than 602 hextillion. And a pound is 16 times heavier than an ounce. So again, it would be much heavier than, it would be much more than 602 hextillion. But whatever number it turned out to be, maybe it would turn out to be, heptillion, the next high multiple. Wouldn't matter. It could be hextillions. It would still give us a conversion unit that we could use to convert between number and weight. Yeah. So the only practical difference would be a different number. If we chose ounces instead of grams, our Avogadro's number would change. It would probably be much higher, but it would still be a number that we could say, hey, this is an amount of carbon equal to its atomic mass in ounces. So that is the mole. Thank you for your attention.